Okay, let's recap a little bit on what we have so far, and I'll show you the pictures that I wanted to show last time, which weren't showing up. So what we did last time was that we did very little with space. In fact, we began by talking about the Wright-Fischer and the Morin models, these kind of workhorses of mathematical population genetics. And we said, well, if we've got very large populations and we measure time in units of I put effective population size here, and if we've got 2 alleles in our population and we write P for the proportion of little a alleles, say, then forwards in time, our proportion of little a alleles will evolve approximately according to this Wright-Fischer diffusion, either with or without selection. So we considered the simple form of genic selection, which gives a nonlinearity like this. And this is modeling just the randomness due to reproduction. So we see these fluctuations in allele frequencies, even when neither genetic type has a particular advantage or disadvantage. And then consistent with that forwards in time model, remember we always wanted to have, consistent with the forwards in time model, we wanted a backwards in time model, because it's backwards in time information that geneticists try to reconstruct. And consistent with this forward in time model is the backwards in time Kingman coalescence, or when we have ancestral selection graph. And in the Kingman coalescent, we just saw that as we trace ancestral lineages backwards in time, if there are currently NT individuals ancestral to my sample, then that NT goes to NT minus 1, so 2 of those lineages coalesce at rate 1 per pair, so at rate NT choose 2. And we saw there are many interpretations of this in the when there is no selection for the neutral model. We can actually interpret this Kingman coalescence as genuinely describing the genealogy, the tree of relatedness of individuals sampled from the population. And when the selection, so that we have an ancestral selection graph and we have some branching as well as coalescence going on, we can't directly make this sort of interpretation. We have to work harder to extract the genealogy, and I didn't show you how to do that. But we can at least say that this relationship holds, which is that if I sample n of 0 individuals to my population at time t, the probability that they are all of the less favoured type, so type little a, that's less favoured because I always think of s as positive without saying so, and I've got a minus sign here. Well, that's the same as if I sampled n of t individuals from my ancestral population and asked that all of them be type little a. So, said somewhat more succinctly, for the ancestral selection graph, the probability that all individuals that I sampled now from the population are of type little a is the probability that all the individuals in my ancestral selection graph, if I cut off at any particular time, are of type little a. Okay, and then we introduced space, and this was the Kimura stepping stone model. And remember that basic model said that our population was subdivided, living in what we call demes, so islands, and the sort of archetypical choice for those islands would be the vertices in Z2, because we mostly live in populations that are distributed across the surface of the Earth, and that's meant to be a caricature for our little subset of R2. And if the effective population size is supposed to be sufficiently big in these demes that within deme, I can pretend that everything's evolving according to a Wright-Fischer diffusion, and here I've time changed back into some real time units to measure time in units of 1 generation instead of in units of any generations. And then there's some migration that goes on between the demes, and the way that we constructed that was we said a certain proportion of individuals in deme I would migrate to deme J in each generation. So the probability that an individual currently in deme I migrates to deme J was Mij. This one's Mji. Okay, let's write it down here. And this Mij is small, so the effective population size times Mij is assumed to be of order 1. So I have a system of interacting Wright-Fischer diffusions. And we saw that dual to that, so what was our consistent backwards in time model? Well, our consistent backwards in time model was the structured coalescence. And that structured coalescence looks a lot like the Kingman coalescence, so there's no selection at the moment here, that we have when 2 individuals ancestral to our sample are sitting within the same deme, they coalesce at a rate inversely proportional to the population size in that deme, and then this is the number of pairs of such individuals sitting in the deme. But in addition, these ancestral lineages migrate between demes, and the rate that an ancestral lineage currently in deme I migrates to deme J, so that the number in deme I goes down by 1, the number in deme J goes up by 1, is given by this weighted quantity. So remember, forwards in time, an individual would move from deme I to deme J at rate mij. So if the backwards in time mechanism were the same, then this would happen at rate mji. But in fact, lineages are drawn towards larger demes. Okay. Now, we also have this interpretation in terms of sampling probabilities, where now we have a vector of allele frequencies. Okay, but we also say, well, it's very nice, the Kimura stepping stone model, and actually we should recognize it's truly remarkable, because this was introduced in the 50s. Now, you guys are too young to know this, but stochastic differential equations were only introduced round about then, right? So at the time when Ito was introducing stochastic calculus, Kimura was using it to prove important things in population genetics, and I find that truly remarkable. I mean, the speed with which impact was achieved. Okay, but it would be more natural to have our population evolve. So these n's, we've taken the effective population size in each of these islands to be a constant. It'd be more natural to have that evolve with time. And moreover, many, if not most populations, actually live in spatial continua. So it would be nice to have a model, wouldn't it, where we were working in spatial continua. And we wrote down our first possible model, and you will observe that we now have grey spots showing up on the screen. So I'm cautiously optimistic. And this model was introduced by Wright and Malaco in the 1940s, and the idea really was to generalize that Wright-Fischer model to a spatial context in the most obvious way. So our population evolves in discrete generations. We suppose that to start with, individuals are just scattered uniformly over two-dimensional space. So this is a Poisson process with a constant intensity. Equivalently, actually, because I've done this on a torus, we've taken 1,000 individuals, each one of them just chose a uniformly distributed point on the torus. And in each generation, each individual produces a Poisson number of offspring with mean 1, and the offspring are scattered in a Gaussian distribution around their parent. So in modern parlance, this population will evolve according to a branching random walk. Now, I can see that there's some real mathematics been going on in my absence while I was writing talks yesterday, so you now know all about branching random walk. But let me show you a picture anyway. So what Wright and Malaco did, this is how we should have been ending the last lecture. What Wright and Malaco did was they assumed that this Poisson distribution of points, this sort of uniform distribution across the plane, was a stationary distribution for the process. So if you looked at this, and then looked away for a few generations and looked back again, it would still statistically look the same. And under that assumption, they were able to make predictions about what genetic variability, what patterns of genetic variation would look like in the population today. And of course, they were still observing that genetic variation through phenotype. So they were interested in really quite simple genetic statistics. So they would, so we'll see what they calculated a little later today, I think. Okay, and their model has been, or the formulae that they came up with to tell us about genetic variability have been incredibly widely used, and they're still used today. So even though, as we're about to see, there's a bit of an inconsistency in their model. So this simulation, done a very, very long time ago now by Jerome Kelleher for a lab meeting, takes the Wright-Malecot dynamic and allows the population, so here's our initial population again, distributed in just uniformly across the torus. And what Jerome did was just allow this to evolve according to the Wright-Malecot dynamic. And after 10 generations, the population size hasn't changed very much. It's still very close to 1,000, but this does not look like that, right? I mean, you're seeing a lot of white space. And then after 100 generations, population is still pretty close to 1,000. Lots of white space. This really isn't a Poisson process anymore. And after 1,000 generations, the population is beginning to crash. Okay. Now, as we said last time, it was Felsenstein who first observed that this was a problem, that the Wright-Malecot model was not consistent with their assumption of the stationary, of the Poisson distribution being stationary. And indeed, in 1 and 2 dimensions, the population exhibits this clumping or extinction. So either your population is dead, either it's died out, or it's exhibiting clumping. And we'll see a heuristic for why that's true in a moment. Okay. And last time, again, we quickly went through these mathematical problems. So we explained the plane in the torus. And if we allow independent reproduction, we saw that getting around the plane in the torus, getting around this extinction clumping phenomenon is not so easy. We can't just specify exogenously the population size and expect the problem to go away. And indeed, we saw that in Jerome's simulation, where the population size hasn't changed very much, but the distribution of individuals is still very clumped. And so, if we want to get around this clumping, we're going to have to introduce some sort of local population regulation. And that means correlated reproduction, which makes the mathematics much harder. And so, the first thing we tried is we tried modifying the stepping stone model. So, because the stepping stone model is somehow the ultimate local regulation, it's saying that the population size is exactly some constant value in each of my deans and it's zero everywhere else. I mean, that's just regulating the local population density. And that gave us a model that was mathematically very tractable. But when we tried to generalize that to a continuum, again, as we said last time, so I'm trying to rush through this a bit, we arrive at a stochastic partial differential equation, and we observe that, first of all, this is not the equation that you would get if you were to rescale a stepping stone model according to a diffusive scaling in 2 dimensions. You'd actually just get heat flow. And second of all, actually, this doesn't have a solution in 2 dimensions anyway, so why even try? So we need another approach. We said all that. And we also explained that the obvious, having failed to scale the forwards model to get anything sensible, the obvious thing to do, given we had a consistent backwards in time model for our stepping stone model, which was this structured coalescent, the obvious thing to do was to say, well, okay, I couldn't scale my forwards in time model. Why don't we try the backwards in time model? And if we can get a sensible limit there, that will probably correspond to a forwards in time model. Sadly, the obvious ways of modifying the backwards in time model don't lead to a sensible, interpretable genealogy. So we kind of gave up at that point, I think.
Sorry, one question?
Yeah.
Going back to the original Wright-Malecot, is this Poisson one a critical? The one is
that's critical. Yeah. So that's the point. That it's the one which keeps the mass constant. So Poisson one has got mean one. In fact, we're just about to use it. Okay. So the Poisson one offspring distribution means that the total population size, if you work in a bounded region, is a critical branching process started from a finite initial number of particles. So no surprise it dies out. And guess what? If you start from 1,000 individuals, it's going to die out around about time 1,000, hence the choice of time and sites in the simulation. And if you increase, of course, if you say, well, I'll have Poisson 1 and a bit, the population grows without bound.
But then do you know that somehow Gaussian distribution is, or like the uniform distribution then is invariant in the supercritical case? Or?
In the supercritical case it's not invariant, and in fact you're still going to see, what's going to happen is that the population density will grow, but it won't grow in an even way. It will grow in clumps, and we'll see actually now. This is a one-dimensional calculation, but you'll see it can be generalized to, well, with more work it can be generalized to higher dimensions. So let's try and understand where the clumping comes from in the critical case. In this, we'll see what we can do to get rid of clumping in a moment. So let's think about the Wright-Malaco model in one dimension, because I say this very naive calculation works in one dimension. And all I'm going to show you some very naive calculations. I'm never going to show you anything terribly rigorous. As my students will tell you, I might know what an answer to a question is, but I won't know how to prove it. So that's their job. So let's consider a single ancestor and think about what its descendants look like going forwards in time. So the number of descendants of that single ancestor is obviously a Galton-Watson branching process, because in each generation, each individual independently is leaving a Poisson 1 number of offspring. And a Poisson with parameter 1 has got mean 1, so as has just been pointed out, that's critical branching. So that says that the probability that individual has any descendants alive at time t is proportional to 1 over t. It's a simple calculation for a critical branching process that has to be true. Okay. And so, if that's the case, then the expected number of descendants at time t, given that I'm alive, so if there are any, there are going to be about t of them. And you can see that just by looking at expectations, right? The expected number of descendants is 1, So that's 0 times the probability that there are no descendants, plus the expected number given there are descendants times the probability there are descendants. So if this probability is 1 over t, I've got to have 1 over t times t is 1. So if my critical branching process has survived until time t, there are roughly t individuals. Now, those descendants are following Gaussian random walks. I mean, they threw their descendants off in a Gaussian distribution around the parent. And admittedly, those random walks are dependent. But sort of, they're not going to be any more spread out than if they followed independent random walks, right? If they were allowed to go their own way, they wouldn't be constrained by their relatives. And if they followed independent random walks, then they would be spread over a region of diameter of order square root of t at time t. So I've got t descendants spread over a diameter root t in one dimension. So they've got volume proportional to root t in one dimension. And so if my cluster survives, its density grows like square root of t. And that's exactly what we see. And so what we're seeing is that not many clusters survive, right? Until large time, most clusters have died. And any that have survived are really very dense, on the order of root t. Okay, so that's where the clumping comes from. Now, in 2 dimensions, this argument just fails, right? Because if you do the corresponding calculation, a region of order square root of t diameter in 2 dimensions has got volume t, so I get t over t, which is 1. But a rule of thumb is whenever you do anything in 2 dimensions, there's a logarithm somewhere that's going to screw things up for you. Okay? So it's log t. And by looking at the variance, actually, you can, a very similar argument shows you that the density of a cluster grows like log t in 2 dimensions. In higher dimensions, you're fine, but we don't live in 3 dimensions, we live in 2 dimensions. Okay, so that's where the clumping comes from. All right, so what can we do about it? We want some sort of local population regulation. We're not very happy with the stepping stone model because it's forcing us to live in these discrete demes, and it's not allowing us to evolve the population with time. So let's modify the Wright-Malecot formula, modify our branching mechanism to make it just a little bit, to stop those clumps. So if the density of the population around me is too high, I'm just not going to have so many offspring. And if the density of the population around me is low, I'm going to have lots of offspring. Okay? That's the general idea. So it's a locally regulated population. So here, angle brackets is going to denote integration. And I'm thinking of my population as a purely atomic measure. So what does that mean? It just means that I'm going to add up around, what this is going to be, the expected number of offspring of an individual at x. So an individual at x is going to look around itself in a weighted way. So there's going to be some h of xy. That might just be an indicator function of the ball of radius 1 around me, for example. It could be something very simple. And it's going to measure the population according to that weighting. So this could literally be a counting measure. I could literally count the number of individuals within some distance of me. And if that number of individuals is bigger than some critical value m, I decide it's too crowded, I don't have any offspring, or I have a reduced number of offspring, so this number will be negative. And so this overall number will be less than 1, so I'll be subcritical. On the other hand, if it's not too crowded, if there are not too many individuals around me, I can have more than 1 offspring in general. If I always had less than 1, then obviously I'd die out. So small and crowded regions, big and sparsely populated regions. And it turns out that if you choose M and H and the dispersal kernel the right way, you can actually get a stable population dynamic. And this is a very old simulation of this done by Franz de Paulus, I think, for a paper which he dedicated to my daughter, so I suppose that makes it nearly 21. Okay, so roughly, individuals, what's this? What do I mean for suitable and enough and smooth enough and all that kind of stuff? Well, roughly the rule of thumb is that individuals must disperse sufficiently quickly relative to the range of the interaction that they're not killed by their own close relatives. Okay. The fact that no 2 of my family are in the same city at the moment, or indeed the same country, I think, shows we're good at this. So roughly, individuals must disperse sufficiently quickly relative to the range of interaction. So we'll see exactly what sufficiently quickly should be, or at least we'll see a heuristic for it in a moment. Okay. So sometimes it's easier to consider scaling limits. This model, the problem is that this is impossibly difficult to do anything analytical. The reason I'm just showing you a simulation. It's very, very hard to calculate with this sort of model with these local interaction mechanisms. And sometimes it's easier to consider scaling limits, and it's also a good thing to do to consider scaling limits, because scaling limits tend to be robust. They tend to approximate a wide variety of local models. So I've written down something which is very, it's not biologically relevant in the sense that you can't take a population and say it evolves this way. On the other hand, it has this characteristic of individuals being more reproductively successful where the population is sparse, which we might think was representative of biological populations. And one might hope, if I can take a good scaling limit, that lots of other models would also be approximated by the same scaling limit. And that's why we take scaling limits, really. Plus they're easier. So for our modified Wright-Malecot model, it turns out that we can obtain a stochastic non-local Fischer Kpp equation. So what does that mean? Well, informally, what we're doing is writing down, what's this? This is the regulation of the population. So this is saying everyone follows Brownian motion, roughly speaking. This is the dispersal around ourselves according to a Gaussian. So I'm going to look at over a very long time scale, so I can't tell, in the same way as with Moran and Wright-Fischer models, I can't tell whether I was working with discrete or overlapping generations when I passed through the Wright-Fischer diffusion. So here, it doesn't matter whether I set up my model with discrete generations or overlapping generations, because from a distance or over long time scales, the motion of individuals is going to look like Brownian motion, and that's where the Laplacian here comes from. This is a local growth rate. Now, let me just skip back for a moment. You'll see that I put an epsilon in here to say that just says this is actually very close to 1, because I'm looking for things that happen over very long time scales, and over very long time scales, the epsilon has gone, and I actually see a sort of intrinsic growth rate. But again, this is saying, if this is negative, then my population locally tends to go down. This would be exponential growth with the negative parameter. If this is positive, locally it looks like exponential growth with a positive parameter. Okay? And then this is the randomness due to reproduction that we see from a branching process. So we've already seen it for the Wright-Fischer model, where we have an XS1 minus XS, but this is for a branching process. Now I wrote down this equation as if it made sense. And actually it does. So whereas when I wrote down the SPD last time, I immediately dismissed it, this one, at least if we allow ourselves to remember that these x's are measures, and so we probably don't really want to take this square root here, makes perfectly good sense. In one dimension, it's a function and it makes sense, but in 2 dimensions, we characterize the process in terms of what's called the Martingale problem. Now, I'm only showing you this because I want to show you the heuristic for the relationship between dispersal and interaction radius, but roughly this is what's called a super process. Very beautiful objects, highly recommend it. Do get royalties if you buy my book. Not many these days. So what we do is we take test functions. So remember that I said think of our xt's as purely atomic measures in the pre-limit. In the limit, these are measures, and they're quite complicated measures, but as long as you keep thinking of them as clouds of particles, you don't go far wrong, and you don't get too frightened by them. So think of this as a kind of cloud of particles. It's somewhere between the Lebesgue measure and a bunch of atoms moving around. But crucially, I can integrate a test function against it. So this is meant to be a positive test function. And it's smooth enough that I can apply a Laplacian to it. And I probably don't want it to get too big at infinity, so maybe we should take it to have complex form. Okay. And then what this expression is, well, it says the difference between the amount, so it's specified with the indicator function of a ball. This would be the amount of mass in the ball at time t, minus the amount of mass in the ball at time 0. This is just saying everything spreads out according to Brownian motion. And this is this kind of intrinsic growth rate. This is saying that it either goes up or it goes down, and it varies with time. If this were a constant, this would just correspond to exponential growth or exponential shrinking. And this quantity is a martingale, so the expectation of this quantity is constant, so 0 in particular. Substitute t equals 0. And its quadratic variation can be written down explicitly, and here it is. So if you haven't seen martingale problems, again, it doesn't really matter. It's a nice way of characterizing the way in which random processes evolve. This is the deterministic bit. This is saying I can predict this part, and this is the fluctuations around that deterministic solution. So if this was zero, we just have a non-local differential equation, and we'd be able to whack it onto the computer. Okay, so let's go back to that clumping, that survival extinction for my modified version of the Wright-Malaco model. And I should say, at the top of the slide it said it. It says a la Bolka-Pacala. This was a model along these lines was introduced by Bolka-Pacala into the ecology literature in the 1990s, I think. Okay. So let's choose our interaction to be a function just of separation. So it could, for example, be an indicator function, and more generally it could be that the influence that other individuals have on me decays with distance. And I'm going to define a further scale version of my superprocess. And what I'm going to do is I'm going to look at, so if I were the indicator function of the unit ball, say, then this would say I'm going to look at time theta squared t at the density, so the average amount of mass in a ball of radius theta divided by theta squared. So that's saying, what does the density of the mass in a ball of radius theta look like at time theta squared t? So it's looking at the large scale dynamics of my population. Yeah. So if h is the indicator function of the unit ball, I'm just saying at some very large, if phi is the indicator function of the unit ball, I'm saying that this scale process is telling me what the process looks like over large spatial and temporal scales. And so if that quantity goes to 0, most likely my population is dying out, and it's certainly going to be something that's clumping. It's not going to have a nice uniform density. Conversely, if it's going to infinity, the opposite is happening. Okay. Now, if I define h in this way, and I look at this scale process, I can again write down the Martingale problem. And the bits in black are exactly what we had beforehand. And so for those of you in the know, where I'm assuming that I'm starting x0 from Lebesgue measure, or from something else which is spatially homogeneous. But Lebesgue measure is as good a place as any. For those of you in the know, you'll know that if I start a Dawson Watanabe superprocess, which is this thing without this term, from Lebesgue measure in 2 dimensions, then it's invariant under this diffusive scaling. Okay. This is the only term that's changed. And what's happened to it? Well, where I had an h before, I've now got this h theta, and moreover, it's having a rather strong effect. So I've got a theta squared in here. So, and the quadratic variation hasn't changed. So if h theta goes to infinity, if this goes to infinity, as theta goes to infinity, I can expect that my population is going to die out. But what does h theta look like? Well, really, that's the same as saying if r squared h of r goes to infinity as r goes to infinity, then I should expect extinction. And it turns out, somewhat surprisingly, that this back-of-the-envelope calculation is exactly the right calculation to do. And one can prove, sort of, someone cleverer than me, Anton Vakorbinger can prove something much stronger than I can prove, but one can prove that if r squared h of r goes to infinity, then indeed you get extinction, and if r squared h of r does not tend to infinity, then you get survival, and you get a nice non-clumped stationary distribution for this model, loosely. I mean, there are some extra conditions and you have to modify the model a little bit, but roughly this is the condition that you need. And this is exactly what the heuristic is saying, I've got to run fast enough to escape the competition from my neighbours corresponds to. Okay. Right. So, but what about ancestral lineages? Because remember, we've got a forwards in time model, so I've said that, at least for some parameter values, we can modify this Wright-Malaco model to have this local regulation of the population density, and we'll get a nice stable population. But the key thing then is that we want to understand what that means for things going backwards in time. And ideally, of course, we like the whole genealogy, but although ambitious, I'm not that ambitious. Let's think first of all about what happens to a single individual. So what's the location of the genetic ancestor at time t in the past of just one individual now? And a key quantity that one needs to understand is what we call the effective dispersal rate. So as I go backwards in time, what's the motion of those ancestral lineages, and in particular, how does their distance from the individual I sampled scale with time? So on average, in this model, it's going to be 0 because everything was translation invariant, assuming I sample sort of uniformly at random, but it's going to have some sort of variance, and the variance is going to be the square of that sigma e. Okay, times t. So we sample an individual from the population in steady state. Wright-Malaco said, well, steady state, that's just my nice Poisson distribution, and forwards in time, everything evolves the same way as backwards in time. So over large spatial and temporal scales, I'll get a Brownian motion, which has the same dispersal characteristics as the forwards in time model. So it's determined entirely by the Gaussian jumps, by the Gaussian distribution in which individuals threw down their offspring. Now, numerically, in that modified model of ours, what we see is that over large spatial and temporal scales, we do approximately get a Brownian motion, but the variance is larger, much larger, in fact, than is suggested by the forwards in time model. So maybe that's not so unexpected, because we said from the stepping stone model that unless the population size is the same in every team, if the population size is the same in every team, which is roughly speaking what Wright and Malaco are assuming, then the forwards in time migration is the same as the backwards in time migration. But we also saw that lineages are drawn towards more densely populated regions. And so maybe what we're seeing in our modified model is that they're drawn towards more densely populated regions, but those more densely populated regions are transient, because we said, well, if it's densely populated, we're not going to allow individuals to have so many offspring, and so automatically the population size will reduce. That's one possible explanation. Okay. But a general question is it generic that as we go backwards in time, in a model in which we allow the population size to fluctuate, we're going to see a larger variance, or might it sometimes be a smaller variance? Is it determined just by these fluctuations in population size? Now, I think I've already confessed that we don't have a clue how to analyse the modification of the Volcker-Picana model with, modification of the Wright-Malaco model with this local population regulation. And even when we pass to a superprocess limit, beyond the calculations that followed from that back in the envelope I gave you, it's very difficult. And so a natural thing is to say, well, why don't we try to get some of these characteristics that we've got for this modification of Wright-Malaco into a discrete space model, because very often they're easier to analyse. And that's the next thing that we're going to do. So this is a model which, I'd like to say a paper, which is introduced in the thesis of Aaron Smith, who graduated a couple of years ago from Oxford, in fact in the middle of lockdown. And it will be the subject of a joint paper with Aaron, Peter Ralph, and myself, and hopefully Bastian Wiederholt, when he's done one more calculation, which will have a very interesting quantitative result about ancestral lineages. But we can prove quite a lot already, so let me tell you something that we can prove already. So here's the model. We suppose that we start from a model evolving in discrete generations. So I'm going to show you the origin of this. And intergeneration time tau n here is just very small. Just think it's very small. And each individual at x, so individuals are on a lattice, think of d equals 2, sometimes I'll write d, sometimes I'll write 2, sometimes I'll write 1. But it's meant to be, this works in any dimension. And each individual, each adult at a lattice point x, independently produces a Poisson number of offspring. But these are juvenile offspring. And the Poisson number is going to depend upon the local population density. Right? From what we've just seen. And then each adult is independently going to die with some probability, which again depends on the local population density, perhaps on the crowding. And then those juveniles, independently, with probability m times tau n, are going to migrate, and they'll go just to a uniformly chosen neighbouring lattice point. And notice that this is scaling, so if you think in your Wright-Fischer model of intergeneration time as being 1 over n in the units we're looking at, remember we needed migration rate times effective population size to be finite, so that's why our migration probability for our juveniles scales with tau n here. And then when it lands at its neighbouring lattice point, that juvenile is still not guaranteed survival. Depending on how crowded it is there's an establishment probability. And so the probability a juvenile is able to establish depends on how crowded it is where it lands. But if it does establish, then that maturation is instantaneous. Okay. So the real novelty in this model is that we're separating out the juvenile phase. And this is very natural, especially if you're interested, for example, in populations of plants. And of course, there are lots and lots of ways that you could generalize things. In particular, choosing a neighboring lattice point is certainly not vital, except for sanity when writing down the calculations. Okay. And then we can arrive at a scaling limit. So let's try and understand where that comes from. Well, migration rates are small. So let's imagine there's no migration for a moment and think about what needs to happen within a particular D. So the number of juvenile offspring, so Poisson with parameter gamma n, and they established with probability Rn. So overall, we've got a Poisson with mean Rn gamma n, number of individuals. That's this. This is the number of offspring produced by an individual, and this is the chance that an individual dies. So we want these two numbers to be close to one another, in particular, because we're going to pass to a scaling limit. If we're going to look over very many generations, we want things to still be very close to critical. And what does close to critical mean? Well, we're looking at things over the order intergeneration times tau n. So an order 1 timescale means that we're looking at 1 over tau n generations. And over that timescale, we need the growth to be bounded. And so we need this quantity to be bounded. So we're going to assume that this quantity, and I've missed out the dependence, but this depends on the local population density all the time. But we're going to suppose that R gamma minus mu divided by tau n converges to some nice function. Okay. What else are we going to assume? So tau m is our intergeneration time, that's going to 0. Eta n is just the mass of an individual. And I don't know if I put that on the last slide. Did I put that on? Yes, I did. So eta n is the mass of an individual. So I'm thinking of having lots and lots of individuals to start with and giving them all a small mass. So that's very much along the lines of, so eta n in our Wright-Fischer model, where we tend to look at proportions, would be 1 over n, right? So eta n would be equal to tau n in that context. And here we're going to suppose that eta n over tau n at least converges to something. So think of this as converging to 1. Think of eta n equal to tau n. And all these things converge. R, gamma, mu all converge to something nice. And then what's in Aaron's thesis, so I should update this and put some plus signs, evidently, is that this model will then converge to a solution to a stochastic a system of stochastic differential equations. So now I'm working on subdivided space. I can write these things down with gay abandon, right? So this is just a one-dimensional, this is just an ordinary Brownian motion. There's an independent Brownian motion in each site. So I don't need to worry quite so much about existence. I'm not looking at stochastic PDEs, I'm looking at systems of stochastic ODEs. So this is where one of the ways in which we benefit when we work on discrete space for a bit. Okay, and then what have we got? Well, this is that intrinsic growth rate that we just talked about. Okay. And this, well, what's this? Well, phi is the total number of juveniles produced. U gamma of u is the total number of juveniles produced if the local population size is u. So this phi 0xs is just saying what's the total number of juveniles produced, and they disperse according to the discrete Laplacian, and then they establish with this probability R. So this is just the individuals that move from one location to another. So this is the ones that arise from migration. And then here's the noise term. So let's try and understand the noise term. So this is just what I just wrote down. So where does this really bizarre thing come from? Well, we're used to something like an x1 minus x. Where does that usually arise from? Well, it usually arises somewhere from the binomial. And that's exactly what's happening here. So let's rewrite. Delta, remember, we're going to take to be 1 for our purposes. So let's rewrite this, this quantity here, mu times 2 minus mu, multiplied by x. I want to think of mu times 2 minus mu as mu times 1 minus mu plus 1. But remember, plus mu. But remember that, you know, R gamma was really almost equal to mu. That was our assumption here, that R gamma minus mu is small. So what I've done is I've written mu times 2 minus mu as mu times 1 minus mu plus mu, and then said, well, actually mu is really R gamma. And now we can see where this really bizarre looking term comes from, because the number of surviving adults is binomial with the success probability 1 minus mu. And remember, in our derivation of the Wright-Fischer model, we worked out the variance of binomials. And so in the limit as n tends to infinity, the number of surviving adults is going to give us a noise term that looks like mu times 1 minus mu times x. And then the number of maturing juveniles, well, that was Poisson with this parameter. But the variance of Poisson is equal to its mean, and so I'm going to see an R gamma times x coming up in this variance. So really we think of this as the two things that contribute to the noise, their deaths of adults and their births of offspring. So it's not as mysterious as it might have first appeared. Okay. And I can recover more familiar looking models. So the analogue of our modification of the Wright-Malecot model would be this, right? Where, because I'm working in discrete demes, I can measure my local, this is just measuring my local population size directly within the deme. I don't have to do that in this model, but that'd be one way to do it. And if I do that, then what have I got? Well, it's an exact analogue of what we wrote down for the super process, except that now it makes sense, because these are Brownian motions on lattice points instead of a white noise. Here's my discrete Laplacian for the spatial motion, and this xs1 minus xs is something that's very familiar from the Fischer Kpp equation, which is an equation we'll see again in due course. Okay. So we can recover classic models from this, but it has these extra interesting features. And I should say the most interesting feature, which I'm not really going to talk about, is this one, because you can get all sorts of really interesting stochastic differential equations and indeed just differential equations, just deterministic limits when you take delta equals 0 out of this, which completely change the dynamic of the model. And so just splitting this juvenile and adult phase in this way is leading us to some very, very interesting models. Okay, but let's have a look at the thing we first cared about. Let's look at ancestral lineages. So that's just a reminder of what an ancestral lineage is.
Sorry, just one quick question. So this last set of equations that you showed, I'm guessing it can be written in the form of a measure valid process and before with an alternative problem?
Yes, if you want to, but the reason I haven't is because now we're working on ZD, so we're working on the lattice, and so this is really a system of stochastic ordinary differential equations. But you could certainly think of each xs as being a measure concentrated on that lattice point.
Will it be similar to the previous process that you showed, the Martingale with the particle?
Well, that's the hope, of course, right? I mean, yeah, the thing you write down would be very, very similar. So you could write down, provided... Okay, so we have written down, and Terence can tell you all about this if you're staying for longer during the workshop. And I encourage you to talk to Terence about this. So we have written down an equivalent to this model in continuous space and pass to a limit, and you do indeed get a super process. And what you have to be careful of is that these quantities have to be, if you really want a stochastic limit, these quantities can't be measured just at a point. It really has to be a function in the same way as with Bulk-Picala, we were measuring things by integrating a test function against the process. Here you need to integrate a test function. You can't just look at xs of x, it doesn't make sense for a super process. You can't define a function of the distribution in that way unless it's a very, very boring function. Right.
And sorry, has it been studied? So this the continuum version?
Yeah. Okay. So the continuum version is well underway. I received a nagging email from Peter Ralph yesterday telling me that we are going to finish this, and he's discovered I'm going to California in a few weeks, and he will be there. This is a several thousand-mile journey in order to nag me, which I consider real dedication to the cause. This paper will appear. So the nice thing in that setting, I'm going to show you the ancestral lineage in this setting now. In that setting, we have a look-down construction which preserves the whole genealogy. Of course, like all look-down constructions, it's completely useless when it comes to calculating anything, but nobody told Tom I said that. So Tom Kurtz is also a co-author on the paper with Terence, as is Peter, and as is another student, Ian Letter. So you can see I gather larger and larger teams of people to write papers for me now. Eventually I'll get a student who finishes one. I'm sorry, Terence, it's nearly there. Okay, it's entirely my fault these papers take so long. So yeah, the paper's done, but the paper's not quite done, but it turns out in the discrete setting it's easier to say things, and we can say a little bit more. So let me show you how an ancestral lineage evolves in the discrete setting. So that looks horrible, that slide, and I spent Well, I spent a bit of yesterday afternoon wondering if I can make it look nicer and decided I couldn't. So, the ancestral lineage, I'm going to write it down conditional on knowing the whole population process over a time interval from 0 to t. And I'm going to suppose I sample an individual from the origin at time t, and I ask how does the lineage go backwards in time? So where was it at all times in the past? And if I take t big enough, that's going to tell me something about the dispersal going backwards. Okay. Well, first of all, how often will that lineage jump? Well, the lineage jumps when it is one of the individuals sitting in the deme that migrated from a neighbouring deme. Right? And what's the rate at which lineages migrate from and established? So for a lineage to migrate from a neighbouring deme, it has to be a juvenile of one of those neighbouring demes. And this is how many juveniles there were in the deme to the right of me, for example. I've just written this down on Z1, I think, actually. Yeah, I've just written this down in one dimension. It obviously works in higher dimensions too, but it's easier to write in one dimension. So think of this as a vector in some dimension. So this is the number of juveniles in my neighbouring deme. If they land on me at X, what's the probability they establish? Well, that's R. So this is the number, and this is the probability they migrated. M is the number that migrated. A half was the probability they migrated to me, because I'm thinking of one dimension. So M over 2 times this is the number of individuals in the population xt of x, so this is at time t, this t arrow means it's at time t before the present. So, sorry, at time t minus t. So this is, time t before the present. So this is the number of individuals that, this whole expression is the number of individuals that migrated in from somewhere else. These are the ones that migrated from the deme to the right of me, and these are the ones that migrated from the deme to the left of me. And the chance that I am one of those individuals is just the total number of them divided by xt of x, because we just sampled uniformly from the deme. We can't see anything, we don't see the history. So this is the rate at which I can expect to jump out of the deme in which I'm currently sitting. And the chance that I jump to the right is just the proportion of these guys that are descended from other demes that came from the right. And that's given by this ratio here. So, just writing it down again, lineages now, this lineage, is going to jump to wherever the fecundity was highest, wherever this function phi, which is the fecundity, it's the population size times the number of juveniles produced. So think of that as the total fecundity in the deme. And that doesn't have to be the same as the population size in the deme, and indeed different parameter combinations will give you the same population profile in terms of just population size. So population size is not everything. Fecundity is more important. Okay. So population size may not be informative about the position of an ancestral lineage. Now, because Bastien hasn't finished his calculations to say just how uninformative it is, I'm going to show you another model. Don't feel I'm getting at you, Bastien. Will do. Let me show you another example of this phenomenon where population size isn't necessarily informative about the position of an ancestral lineage. Now, I'm going to go to one dimension. I don't really approve of one-dimensional models, as I'll explain tomorrow morning. They're not necessarily very representative of what's going on. But on the other hand, they can be much easier to work with and useful to play with. So I imagine quite a number of you have seen this equation. This is the Fischer Kpp equation. It was introduced by Fischer in the 1930s to model the spread of an advantageous allele through a population. I say everybody says Fischer Kpp. I feel I should put on record that Kpp did not consider this nonlinearity. They have squared here. It has the same behaviour, but they considered u times 1 minus u squared. And very few people seem to have observed that what they do is they say, we've read the paper of Fischer, and the paper of Fischer says we should look at u times 1 minus u squared. And that's because they were looking at a diploid population, not a haploid population. Okay, that's the Fischer Kpp equation. We are going to modify the Fischer Kpp equation in this way. So we're going to add a nonlinear, we're going to multiply by something that looks like this, where alpha is some parameter between 0 and 1. Now, this is still an equation that can be used to model the spread of an advantageous allele through a population, but it includes something called an allele effect. when the population density is too small, less than 1 minus alpha over 2, this growth rate is negative. So in particular, if I have a travelling wave solution, which this equation does have, I'll write it down in a moment, then out in the front of the travelling wave, the growth rate is actually negative. And so the fact the wave gets pushed forward, there's the travelling wave, and it's pushed wave. The fact it gets pushed forward is because of growth in the bulk. So, maybe because I wished I'd given board talks, but I didn't. So, there's my travelling wave, and Fischer Kpp, classically, it's what's going on out here, which is dragging the wave forwards. The growth rate here, in Fischer Kpp, is much bigger than the growth rate per individual here. If I'm lucky enough to be born here, I'm going to produce a large number of offspring, and that pulls the wave forward. In this equation, the maximum growth rate is somewhere back here, and it's the fact that it just gets too crowded in the Laplacian that pushes us forward. So it's a different sort of wave. This is called a pulled wave, because it's all determined by what's going on in the front, and the wave speed is the Fischer wave speed, as it's known. This is what's called a pushed wave, and the wave speed will typically be much faster, actually, than that for the Fischer wave. Okay, and in fact, for the parameter values that I've chosen, for that alpha small enough, there is a unique travelling wave solution that links 1 at minus infinity to 0 at plus infinity, and it takes up to a translation. It takes this form. Okay. So notice in particular, maybe I even wrote it, I did, how about that, that the shape of this is independent of alpha. All alpha is doing is telling us how quickly we're moving. So for a lot of different values here, for a lot of different nonlinearities here, I'm getting the same shape for my travelling wave. The total population size looks the constant, it looks the same. Right. Okay, so let's see what the implication of that is for where individuals came from, for ancestral lineages. And this is taken from, these pictures are taken from Rockenstein and PNAS in 2012. And what they did was they started, this is the Fischer Kpp equation again. And what they did was they split the initial condition. The initial condition we look at is always going to be the indicator function of the left half line. And you can see that, I hope you can see better than I can, that this is striking, right? So what they've done is they've split the left half line into a bunch of intervals, and they've divided the solution to the Fischer Kpp equation into a bunch of solutions UK, where UK is the solution started from the indicator function of the kth of these intervals. So this light grey, if that's U1, then du1 by dt is dt2, is Laplacian u1, plus u1 times 1 minus u, where u is the sum of all the UKs. So what this trick does is it allows us to keep track of where individuals are descended from. They call it tracer dynamics in physics, and the idea is that you stain individuals at time 0 according to where they're living, and you look at where their descendants sit at a future time. And this top picture here, this is the Fischer Kpp equation, time 40 apparently, and you can see that the whole of the front of this wave is occupied by the descendants of this first stripe here at time 0. Okay. But then they added an Elie effect, as we did on the last slide, slightly differently parameterized, for which apologies. And what you see now, so this is their Elie effect with rho as 0.2, and this is the Elie effect with rho as 0.4. And remember, these waves, we've just checked, are exactly the same waveform, or at least they evolve into exactly the same waveform in 40 spike. And this is at time 150, and this is at time 400. So the wave shapes here are the same. But you can see that the bigger the Elie effect, the bigger the rho, the more different subintervals here are represented at later times. So the genealogy, and this is somehow a proxy for genealogy, right? It's telling me where a lineage came from, and where a lineage comes from is going to be quite different in these different models, even though the population front is going to look the same. When one adds noise, so because these are deterministic equations, we never see coalescence. The coalescence that we see in the Kingman coalescent and its duality of the Wright-Fischer model, as we said at the end of the last lecture, is all in the noise. It's the coalescence comes from the randomness due to reproduction. If you come up with a noisy version of these models, then you do get radically different genealogies. And for those of you who know about this stuff, in the Fischer Kpp case, if you sample individuals from the wavefront when there's a small bit of noise, then you get a coalescent called the Boltzhausen-Schnittmann coalescent that we may encounter later on. Whereas if you have this kind of an Lie effect, then Sarah Pennington wrote a paper in which we have a model that mimics this with a very small noise term added, and the genealogy is in fact a Kingman coalescent, which is completely different from a Boltzhausen-Schnittmann coalescent. So even though we've got an expanding population, it's a population subject to selection, we don't get a Boltzhausen-Schnittmann coalescent, which is what used to be believed would happen. And this is actually rigorous because Sarah wrote it. So that's actual mathematics. Okay, it's also very, very long, so you may not want to read it. But I think this is an important message. If you don't really learn anything else, learn this, that population size isn't everything. Okay, so let's outline the problems of the model so far. Stepping stone model, I didn't like it, and this is only the spatial model. So stepping stone model I didn't like because my population is subdivided, and the size has to be exogenously specified in each of those deans, each of those islands. The Wright-Malecot model, very nice model, except that the assumptions being made are inconsistent, and in fact we know that we're going to get this clumping extinction phenomenon in the interesting dimensions, which is 1 and 2. So the pane in the torus that Felsenstein observed. Wright-Malecot with local regulation, the one we've been talking about a bit this morning, it overcomes the clumping, but there's no known expression for the ancestral lineages. In fact, it's probably hopeless. The discrete model with the separate juvenile phase, there is an expression for the ancestral lineage, but it depends on knowing the history of the population. And the problem is that the population model is not reversible in time. So, it's not looking great, is it? And we've also learned that knowing how the population density evolves is not enough to determine the behaviour of the ancestral lineage. Okay, back to basics. So let's start again. So I told you that Wright and Malaco produced a formula that has been incredibly influential and important. So let's actually think about what that formula does. So what it is concerned with, what it's exploiting, is the fact that there is information about the genealogy in patterns of neutral variation. And what we're going to be interested in is the genealogy of a sample of size 2. Let's not be too ambitious. And the only information available in the genealogy of a sample of size 2 is how long do I have to trace back, how many generations do I have to trace back before I get to the most recent common ancestor. If I sample 2 individuals at a separation x, how far do I have to go back until I hit their most recent common ancestor? And the way that we would observe that through the patterns of neutral variation, the way that Wright and Malaco set it up is that they set up what's called the infinitely many alleles model of mutation. And what this says is that in each generation, independently, with small probability mu, each individual mutates to a type never before seen in the population. Infinitely many alleles means that whenever there's a mutation, it's to a completely new type. And if that happens, then the probability that the 2 individuals that I sample from my population, how can I have lost a piece of chalk I picked up 2 minutes ago? Amazing. I'm out of practice with chalk for some reason I can't quite remember. Actually, we're not allowed chalk in Oxford. Everybody has to be equally disadvantaged, so the Equalities Act says we have to use whiteboards. I was also told once that James Clerk Maxwell invented the whiteboard, to which I'm rather proud of myself for responding very quickly, but sadly he did not invent the whiteboard pen. Okay, so suppose I sample 2 individuals, and I trace backwards in time. I'm a bit schizophrenic about which way is backwards, so let's go this way. All right, so these guys are going to be evolving in some way. And then, at some point in the past, they have a common ancestor, right? So, this time t is the time to their most recent common ancestor. The chance that these guys are of the same genetic type is the chance that there was no mutation along either of these ancestral lineages. If there was a mutation, it was to a type that's never been seen before, and so it's only inherited by one of them. And in this approximation, right, the probability that there is a mutation in any generation is roughly twice mu, because mu is very small, and so the probability of no mutation since the most recent common ancestor is approximately e to the minus twice mu t, if we happen to know when the most recent common ancestor was. And what Wright and Malaco found, based on their assumption that the Poisson distribution was stationary for their model, was an expression for the way that this quantity, so t is random, so I'm going to put an expectation in, and it's going to depend on the initial separation, so I'm going to put a subscript x to mean a vector which tells me about the initial separation. And they found an expression for the way that this quantity decays with x, because the further apart individuals are, the less likely they are to be the same type, because the time to their most recent common ancestor is going to be longer. So that's the quantity that they went for. I think we're going to try and do the same thing. But notice that this neutral mutation rate is really dictating the timescale over which we can reconstruct information about genealogies. And it's perhaps worth saying that if these individuals are sampled very close to one another, they probably coalesce very quickly, so there's probably very little information in there anyway. So the Wright-Malecot formula is not going to be particularly relevant if we sample individuals very, very close to one another, but it will be relevant if we sample individuals from further apart. Okay. So let's see how we might calculate the probability of identity, and we're going to do it for a subdivided population, and we're not going to be complicated and have juveniles and maturing and so on. We're just going to do something Wright-Fischer-like. So I'm going to work with a population on Z2, n individuals per deme, discrete generations. And the reproduction within a deme is going to be Wright-Fischer. So remember that just says that each offspring chooses its parent uniformly at random from the previous population, and it adopts the type of that parent. And I'm going to suppose that a proportion g1 of x minus y of offspring in deme x migrate to deme y. Okay? And we'll later take this to be a Gaussian. And the one here indicating that is one generation, as we'll see. Okay, and then we want to, we're using this notation, so t is going to be the time to the most recent common ancestor, MRCA, of sample of size 2. And I'm going to write f of x for this quantity that we'd like to calculate, and actually I'm going to approximate it by saying that this is e to the minus twice mu t in due course. Okay, so how are we going to calculate that? Well, the first thing we might try and calculate is what's the probability that the most recent common ancestor was at time exactly little t generations in the past. And I can do that for t equals 1. So if t equals 1, the probability that my individuals had a common ancestor is, well, first of all, they've got to have had their parents in the same deme. And remember, individuals were migrating according to this kernel. So the probability that they both came from the deme labeled Z is, well, one of them had to go to X, so without loss of generality, because this is all spatially homogeneous, I'm going to suppose that one of my individuals is at the origin and the other is at X. So the individual at the origin would have needed to go to deme Z. The individual at X needs to go to deme Z, so the probability of both of those things happening is this. It could have been any deme, so I integrate. So I just get the convolution of G1 with itself, and that's what this capital G1 is going to be. But then having both come from the same deme isn't quite enough. They've also got to have had the same parent in that deme, and the probability of that is 1 over n, where n, remember n is the population size in each deme. Okay. So that's one generation. And now I can write down a recursion. You see, if t is bigger than 1, if I'm looking at generations beyond 1, I'm just going to partition over the location of the immediate ancestors. So this G1 just says, you know, what's the probability that the separation, which is x now at time t, was x minus y at time, sorry, was y at time t minus 1. So this is just again a convolution And it's telling us that the separation over one generation has changed from X to Y. And now I want to know, well, what's the probability that the individuals that are now at separation Y had a common ancestor exactly t minus 1 generations in the past, and that would be psi t minus 1 of Y. But I've got to be a little careful, because if they did happen to go into the same D, right, so if Y was 0 here, they might have coalesced. So I've got to subtract off the possibility that they actually coalesced. Right? So if they've already coalesced in time 1, they certainly didn't coalesce at a time t bigger than 1. Okay? So that's a recursion which relates psi t to psi t minus 1. Right? And that can be solved. And believe me, I was not going to type up the solution. So if you sit at your desk, you can write down this expression. See? So all that's happened is you just keep iterating. Just keep iterating this. So now we've got an expression for psi t as a single object based on the t-fold convolution of my Gaussians. And this convolution of G with psi. Now, whenever you see a convolution, yeah, come on, we've all done those second year undergraduate courses. We all go off and we want to take a transform. So why don't we take a Laplace transform? And of course, the reason is because we're working in discrete generations, so we can't do what we usually do. We have to take a discrete transform. So let's get some notation. So let's call G tilde the discrete Laplace transform of t. So that's this expression. So this is an exact, if you think of this as e to the minus zt, and this is an integral, I've really taken a Laplace transform and evaluated it as e. Okay. And if I do that, that convolution is going to turn into a product. And now, see, if I write phi of zx for this expectation, which is almost what I'm trying to calculate, but not quite, then just substituting into star, and just taking this Laplace transform here, so multiplying by z to the t and summing, I see that I can write it as 1 over n times g tilde times 1 minus phi of z and 0. So the convolution became a product. Okay. So that's what we've got to. And now I put x equals 0, and that gives me an expression for phi of z0, right? And there it is. And then I substitute back in again, and that gives me an expression for phi of zx. And that's looking really good, because now if I just know what g tilde is, I'm done. I've got an expression for phi. Now, turns out you can sometimes write down g tilde. So if my dispersal was approximately Gaussian, then it turns out that one can write down these g tildes and evaluated at 0, we get this thing with a logarithmic divergence, and evaluated at x, we get something which is horrible. I mean, these are approximate because I've replaced my discrete Gaussian by a continuous Gaussian, so I've replaced my discrete dispersal by a continuous dispersal. But if you're willing to accept that, then you can solve exactly, and we get a modified Bessel function of the second kind of degree 0. Can't beat it. And this script n is what's known as Wright's neighborhood size, twice n pi sigma squared, and it's absolutely crucial quantity. Sorry, it'll appear on the next slide. It's an absolutely crucial quantity because what does it mean? Well, it's roughly speaking, if I'm an individual alive now, how many potential parents did I have to choose between? And it tells me something important about the rate of coalescence. Okay. So what have we shown? We've shown that just substituting, we've shown that phi satisfies this. Problem is, if you let z tend to 0, this all goes horribly wrong and it diverges because that Bessel function's a mess. And so what we do is that we assume that there's some small, that's meant to say x goes to 0, I do apologise. Assume that the solution is actually constant. You see, as x goes to 0, I'm getting k0 of 0, and k0 of 0 is not well behaved because the Bessel function blows up logarithmically at the origin. So what we do is we suppose the solution is constant over some small scale. We already said that if individuals are close together, we might as well do that because there's not going to be a mutation between them anyway. And we use this asymptotic behavior of the Bessel process and do a bit of rearrangement, and we obtain an expression of this form, and this is what's known as the Wright-Malaco formula. Okay? So in some sense, it's not a very difficult derivation, but it does make one or two assumptions. So how does it do? You see, what's interesting is that the Wright-Malaco formula, not only is it applied widely for populations distributed across the two-dimensional space, so they derived it for their two-dimensional model, but this is how well it fits. So we sent it down some approximations. This is how well it fits a nearest neighbour stepping stone model. So obviously things are going to go wrong at the origin. These three lines correspond to three different effective population sizes. Other than that, things are the same. Migration rates are the same in each of these. And don't ask why these dots are a different colour from these dots. I mean, these are somehow off diagonal. So the black dots involve starting at the origin and going out along the x-axis in a two-dimensional space. So this is a two-dimensional model. But you can see that the fit of these curves, which are the Wright-Malaco curves, is astonishingly good, right down to a separation of 1D. And I can't remember how big the population sizes were, but they weren't astronomical because these simulations were done a long time ago. Okay, so that suggests that there ought to be a nice way to write down a continuous model which is consistent with Wright and Malaco. So although their model was inconsistent, there ought to be a way to write down a model that makes these consistent. Okay. Now, question is already. Let me show you some of the. So we saw some of the mathematical problems that we wanted to overcome in the Wright-Malaco model, the clumping and all that kind of stuff. But what are the biological problems with it? Well, some of the biological features that we'd like to incorporate into a spatially continuous model are things like the following. So, genetic diversity is much lower than expected from census numbers. What do I mean by that? What I mean is the effective population size. The effective population size is a proxy for genetic diversity. So, the effective population size of natural populations tends to be very, very much lower than the census population size. So for humans, there's a 5 order of magnitude difference. Effective population size 10,000, how many billion living on the planet? So that's one thing so we want our model to be such that if we calculated an NE, we would get something much less than census. Another thing is that allele frequencies are actually correlated over long distances. So in the Wright-Malaco model, what we see when we're away from that rather irritating singularity at the origin, of course I should have said, I mean, this can't be a probability of identity because probabilities are always at most 1, right? So the fact it goes to infinity does indicate something's gone a bit wrong. I had a student in Edinburgh who submitted a problem sheet with the answer, the probability of x is 10 to the 32. And I suggested there was a bit of a clue that you might have made a mistake. I did have a beautiful picture of this, but okay. So what the Wright-Malaco formula says is that when we're away from the origin, this decay is actually essentially exponential. That's the way that the Bessel function behaves over sort of intermediate scales. But what happens when we actually look at data is very often we do see an exponential decay over intermediate scales, but then when we get to very long scales, we get a fatter decay. The probability does continue to decay, but it decays less quickly. So it's a different exponential rate. Now, I had a beautiful slide of this with human population data, but for some reason, whenever I tried to convert it into something that LaTeX would read, the computer crashed. So I'm afraid you can't see that. But there's some human population data which illustrates this rather beautifully. So you get an exponential decay and then a slower exponential decay. And those two things, these two features, can both be explained by the fact that the demographic history of many species is actually dominated by large-scale extinction and colonization events. And I'd like to demonstrate this, I'd like to illustrate this with this map. This is where the last glacial maximum was 18,000 years ago. And I can tell you it would have been a good deal colder in Bonn then than it is today. So much of Northern Europe, most of Northern Europe was covered in ice. And so, and many species, especially species of plants and things, retreated to refugia. And then extraordinarily rapidly, when the ice retreated, those species spread again and recolonized the regions that have been abandoned. And that's one of the possible ways that we can explain these rapid recolonizations. It's one of the possible ways that we can explain both this long-distance correlations and this lack of diversity, where there was a kind of a bottleneck and then an expansion here. And I guess actually we should talk to Marta and Jerry about the effect of extinction recolonization events on populations, because I think they're thinking about exactly that at the moment. Okay. Another thing that we're going to incorporate into our model, which is something which we haven't incorporated so far, is that if you're in a spatial continuum, so far when we talked about the Kingman coalescence, we said, well, you know, that our population size was very big, and as a result of that, we found ourselves, at least if the sample size was less than n to the 1/3, able to ignore simultaneous and multiple mergers. So we never had 3 or more lineages coming together in a single generation in our model. But if we're in a spatial continuum, a single individual can be parent to a significant proportion of the local population. This is dandelion greens, and my backyard looks very much like this. So, you know, these plants, there are actually many, many plants here, and they almost certainly came from a common parent because of the way that dandelions spread their seed in these beautiful clocks, which then tend to stick together as they go apart. Okay. So we're going to look at a model which incorporates those features, and what we're going to do is we're going to start with an individual-based model. So biologists are always right, so you should always start from where they tell you to start from. And Wright and Malaco told us, start from something with Poisson with a constant intensity. So that's what these things meant to represent. And what we're going to do is that we're going to have our population reproduce. We're going to have overlapping generations because we're working on all of ZD, and it makes it R2, and it makes it easier. But we're going to base reproduction not on individuals, but on events. And the way this is going to work is that we're going to throw down events at a particular rate. So this all looks very scary, but it's not really scary. So this says that at a rate which is constant in time and homogeneous in space, I throw down balls which have a random radius r, and for each such ball, I also draw a number u. And that number u is going to be a probability, and that probability sits between 0 and 1. And what does it tell me when I get to such an event? Well, when such an event falls, I'm throwing a ball down on the plane, and here's the centre x and the radius r. And if there aren't any individuals living there, I just forget it, I don't do anything. But if there is an individual living there, I choose a parent uniformly at random. So what I've done is I've stained this one magenta. Each individual in the region dies independently with probability u. So remember, u is a probability, so each of these guys just flips a coin, and if it comes up heads, they die. The parent may die, they haven't in this example. And then I replenish the population within the ball by throwing down a Poisson process with constant intensity. But the intensity now, so it's only within the ball, so it's the indicator of the ball is sitting here. And it's not lambda, but it's lambda times u in order to approximately replace the individuals I just killed. And of course, if it weren't for this, if I threw away this condition about if the region's empty, do nothing, then actually the Poisson process with constant intensity would be the stationary distribution for this process. Because I would be throwing away exactly a Poisson lambda u indicator of the ball number of individuals and replenishing by them. However, biologically, we don't really expect that if a region is empty, we get births from nowhere, and so we feel it's quite important to keep this condition in the model. Okay? And offspring inherit the type of the parent. So here I've thrown down a couple of offspring, and they've inherited this magenta type. Okay. Now let's see what happens to that if I let lambda tend to infinity. And I'm going to show you what the limit should be by considering what happens when there's no space. So when there's no space, what are we doing? Well, we're starting from a Poisson lambda number of individuals. And when a reproduction event falls, I'm going to kill a proportion u. So each individual flips a coin, comes up u. No, it comes up heads with probability u. If it comes up heads, right? So I'm going to kill a proportion lambda u, which means that the number of survivors is going to be Poisson 1 minus lambda times u, and there are going to be Poisson u lambda offspring. Now, one of the many nice things about Poisson processes, they're the main reason we do probability, because they are so nice, but one of the nice things is that the variance of a Poisson is equal to its mean. So as lambda tends to infinity, the proportion of individuals that die and are replaced, so this Poisson u lambda divided by the total number we started with, is going to converge to u, because the number of individuals that die is lambda u plus an error of the order of the square root of lambda times u. So as lambda goes to infinity, that lambda u is what's going to dominate. Okay. As a result, as lambda goes to infinity, this is converging to something deterministic. Now, if I hadn't chosen a Poisson here, and I'd chosen to replace with something other than a Poisson, I can get different things happening. And if you want to know some of the different things that happened, you talk to Julian, who's worked on precisely this, and he'll tell you it can get quite difficult. But if, for example, I chose a geometric number of offspring with the same mean, then I would still have a random proportion of the population replaced. In fact, the random number, and that random number would converge to an exponential. Okay. So, right, that's what happens in a single event. And so you can imagine that if I do this without space for a whole Poisson process of events, I'm going to arrive at a stochastic process which is relatively simple to describe, and we're going to call it the Lambda-Fleming-Viot process. It's a name that was adopted by, sort of adopted by both Wright and Malaco. They call these generalized Fleming-Viot processes. And how does that work? Well, first I need a state space, and up to now our state space of genetic types has tended to be little a, capital A, but it could be anything. Indeed, we took it to be the infinitely many alleles model, which you could think of as being the unit interval in the Wright-Malecot formula. And what the state of our Lambda-Fleming-Viot process is going to be is it's going to be a probability measure on that type space. So in the simple case of little a and capital A alleles, it would just be the proportion of individuals that are little a. Okay? So K here is the space of genetic types, M1 means probability measures. Events are driven by a Poisson point process, intensity homogeneous in time, and now I just need some measure on the impact, right? And if I reach an event in pi, then an individual is sampled at random for the population immediately before that event. In other words, I choose a genetic type according to rho at time t minus. And I replace a proportion u of the population by offspring of that chosen individual. So when I update my probability measure, I'm going to have, these are the survivors, so 1 minus u times what I started with, but u times a point mass on the type of the parent that I chose. And it turns out that this is a well-defined process if f is in a special form, and that special form is it has to take the form lambda of du over u squared, where lambda is a finite measure on 0, 1. And this process first appeared in a paper of Donnelly and Kurtz in 1999. Okay. Now, have I got time? Yeah, time to do this. Let me just finish this lecture by showing you what happens backwards in time. So first of all, a picture speaks 1,000 words. So what we said on the last slide, here's my Poisson process of events. So all I've done is I've thrown down a bunch of points which are falling at a constant rate in time, and each of them is specifying an impact u. Right? And I'm showing you down here, I'm showing you what happens at this point. And the impact was this value u, and it happened at time t. Now, immediately before the event, I'm supposing that the proportions of individuals in my population, my type space has got 3 colours, it's these 3 colours, and these are the proportions. And I threw down a uniformly distributed point on 0, 1, which is equivalent to sampling a type uniformly from here, and it fell in this cyan region. So that tells me all the offspring of my event are going to be cyan. A proportion 1 minus u of the population survive. So the ratios between these colours here, above this line, are the same as the ratio there. And these guys are the offspring of the event. And now I can also tell you what's going to happen to ancestral lineages as I go backwards in time through such an event. Because suppose I take a sample, and I've taken here a sample of size 5, that I just sampled uniformly at random. from the population after the event. And I ask what happens to those individuals as I go back. Well, the probability that exactly 3 of them coalesce, as I've shown here, is the probability that exactly 3 of them are among the portion of the population that are offspring of the event, so this portion U here, and the other individuals, the individuals that were not offspring of the event, just passed through unharmed. Right? And what's the probability that this did happen? Well, the probability that these 3 fell here was just U cubed, because they're just uniform picks. We don't know anything about their type, we're just sampling uniformly from the population. So the probability that 3 lineages fall here is U cubed, and the other 2 falling here is 1 minus U squared. And it turns out that this kind of coalescent process, which allows, notice that we have 3 lineages merging at the same time. This kind of coalescent process was written down by Donnelly, Kurtz, Pittman, and Sakharov all at the same time. This is the same paper in which Donnelly and Kurtz first wrote down the Lambda-Fleming-Viot process. And if there are currently n ancestral lineages, each transition involving a particular j of them merging happens at a rate that can be written in this way. So let's just understand this rate, and then we can stop. Well, the probability that exactly the j individuals that I've chosen merge is the probability they are offspring of the population. That's u to the j. And I don't want anyone else merging. I'm only interested in the transition in which exactly these j guys merge. So I want the other n minus j individuals to all fall in the other part of the population. And that's 1 minus u to the n minus j. So that's for a particular event. And then the rate at which I see a merger of this type, well, I integrate against the rate at which I see mergers with impact u. Sorry, I see events with impact u. And that, we said, could be written as lambda of du over u squared, where lambda is a finite measure. And of course, there's a combinatorial constant. Here I'm supposing it's a particular j lineages that merge. If you want the probability that I see j lineages merging, then there'll be an n choose j out front. And just to convince you that this isn't anything particularly new to us, if I take lambda to be an atom on 0, then I recover the Kingman coalescent. Right? So if lambda's an atom on 0, then what's going to happen? Well, merging doesn't make sense unless j is at least 2. If j is exactly 2, that 2 cancels with that 2. And then 1 minus u to the n minus j integrated against delta 0, well, that means u is 0, so that gives me 1. So for each pair of lineages, I've got rate 1. If j is bigger than 2, so if j is 3, say, then u to the j minus u squared is going to leave me with a positive power of u, and when I integrate against delta 0, I get 0. So I'll never see multiple mergers. Okay, so this is a model to keep in mind without space, and then this afternoon we'll talk about what happens when you modify this to take space into account. Okay, thanks very much.